Hey guys, welcome to another day of chemistry. Let's get started. Today we're going to be talking about what I believe to be the hardest part of ionic bonding, which is talking about tertiary ionic compounds. But before we get to that, I wanted to review something that's also kind of difficult, the idea of multi-charge metals and kind of how to name them and what that all means. Oops. Okay, so we got two questions for you. Go ahead and pause the video and try these out. Great, hopefully you take some time to do that. Let's go over them. So the first question asks, what's the charge of the metal in the compound cobalt phosphide? And this one right away is kind of a trick question. If you look on the back of your periodic table, what you'll see here is on the ion list is that cobalt 4 plus does not exist. So you have two options then. You've either got cobalt 2 plus or you've got cobalt 3 plus. Or you could say we don't know. Now in this case, the answer here, since cobalt 2 plus is a possible charge of cobalt, and cobalt 3 plus is also a possible charge, the answer is actually D, we don't know. So you will never see something like cobalt phosphide written out. Instead, what you'll see is right in the middle here, you'll have to have, in parentheses, a Roman numeral. And that Roman numeral will either be 2 or it will be 3. Once you have a Roman numeral there, then you can tell whether it's a cobalt with a charge of 2 plus or a cobalt with a charge of 3 plus. But we'll never write out something just like cobalt phosphide, because for cobalt specifically, that specific metal, you have to be more specific because it has two possible charges. It could either be 2 plus or it could be 3 plus. So then, taking a look at the second, is the answer just we don't know? Unfortunately, that is not the answer. In this case, if you look at the back of the periodic table, what you'll see here is that it's not 3 plus, it's not 4 plus, and it's not we don't know. The only charge for cadmium is 2 plus. So the takeaway here is that you must use a Roman numeral when naming a multi-charge metal, or a metal that could be 2 plus or 3 plus. It could also be 4 plus or whatever. It doesn't have to be specifically those two. But when you have a metal like cadmium that only has one charge, and again, you look at charges by looking at the back of your periodic table at that ion list, then you know in this case, no Roman numeral is needed. So sometimes you use a Roman numeral, sometimes you don't. And it's up to you to use that ion list to figure out when you do and when you don't. So hopefully that helps clear it up with transition metals. Sometimes you do, sometimes you don't. Look at the ion list to figure it out. Okay, and this is just kind of explaining those rules once again. Metals with more than one possible charge need Roman numerals in their names, and metals with only one possible charge do not need Roman numerals in their names. These are kind of two good facts to know, two good facts to have written down in your notes somewhere. Here are examples of manganese 6 oxide, manganese 4 oxide versus manganese 2 oxide. In both these cases here, different formulas, and those different formulas exist because they have different Roman numerals here, which means manganese in this top case has a charge of 4 plus, and in this bottom instance, they're going to have a charge of 2 plus. So that's why we have two oxygens here. Oxygen in both these cases has a negative 2 charge. So yeah, that's why we have 1 and 1 here, so they cancel out, versus 1 and 2 here, because they cancel out again. Okay, metals with one possible charge do not need Roman numerals in their name. So for example, Al2O3, we would just say that's aluminum oxide, because aluminum only has that 3 plus charge. Again, oxygen in this case is 2 minus, aluminum is 3 plus, so that's kind of where we see the Al2O3. So that they both here have charges of 6, positive 6 and negative 6. Hopefully you know how to get charges. Hopefully you know how to, from a formula, derive a name, or how to, from a name, derive a formula. What we're going to do is we're going to throw another wrench into this, and we're going to make it a little bit more complicated by talking about things called polyatomic ions. We're going to skip this review for now. But those are answers, so if you wanted to, you can go back and try those problems. Tertiary ionic compounds, again, they talk about these things called polyatomic ions. There's that word poly, which is either Greek or Latin, and it means more than one. So polyatomic ions are going to be ions that are made up of more than one atom. So an example of that would be something like NO3 1 minus. NO3 1 minus is called nitrate, and this is a group of atoms, 4 atoms, 1 N and 3 O's, that always forms an ion together. So these 4 atoms kind of act the same way as like Cl1 minus would. Now Cl, keep in mind, is just 1 atom, but NO3 is 3 atoms. So they behave in the same way. We're going to match them the same way. They're going to bond the same way. But now we just kind of have to write them a little bit different. Instead of, like, let's say we have 3 Cls, if we had 3 NO3s, here's what it would look like. It would look like NO3, 3, which kind of almost looks like NO33. So what we're going to do then, when we have 3 of these NO3s, is we're just going to put NO3 itself in parentheses. So we'll talk about parenthesis rules in a bit, but anytime you see a polyatomic ion, what I like to do is I like to substitute it with something like Cl, or maybe it's something like O. O has a charge of 2 minus. Or maybe it's something like, I don't know, N. N has a charge of 3 minus. So you can kind of substitute any polyatomic ion with a 1 minus, a 2 minus, or a 3 with Cl, O, and N, and that'll kind of help you get rid of some of the complex parts. The part that people struggle with the most is the parentheses here. So let's get into some examples. Okay, polyatomic ions are a group of atoms that have a charge. That's a definition worth writing down. The formulas can't be adjusted. The names are just given. So if you have something like NO3, you can't change that to NO2 just because NO3 is called nitrate. NO2 is a different polyatomic ion, for example. And here are 3 examples of different polyatomic ions that you're going to need to know. NH4 plus ammonium is definitely worth noting in your ion list. It's the only ion that has a positive charge. So that's something that's unique. So you might want to write down NH4 plus ammonium and just know that it's the only polyatomic ion that's positive. All other polyatomic ions have a negative charge, either -1, -2, and some of them are even more crazy, like -3, -4. I don't know if there's any -5s, but I think there is a couple -4s. But mostly -1, -2, or -3. Okay, so here are 2 examples of polyatomic ions with 2 different compounds here. You'll notice that in this problem, the polyatomic ion that we're working with is CO3. It's called carbonate, and CO3, as you may have guessed by the fact that we have 2 NAs over here, CO3 has a -2 charge, and Na, of course, has a +1 charge. So in this case, we just name Na. Na is sodium. We name CO3. CO3, if you look on the back of your periodic table, you'll see that it's called carbonate. And so look up the name for CO3, carbonate. Look up the name for the cation, sodium, sodium carbonate. And that's all we have to do here for this problem. Pretty simple, just 2 steps. Name the anion, name the cation, name the blue stuff, name the red stuff, name the metal, name the non-metal, and you're done. Pretty straightforward. For multi-charge metals, the process is a little bit more complicated because you have to use what you know about the polyatomic ion to figure out what the charge of this metal is. Remember, Fe can have 2 possible charges. It could be a 2+, or it could be a 3+. So we're going to have to figure out in this specific instance, is it 2 or is it 3? First, the first rule is the same as the rule before. You look up the name of the anion, which in this case is carbonate. So that first rule for both these cases is identical. Now, the second rule is that we have to name the cation, but we have to figure out that Fe is in fact a 3+. Here, if we look, we know that carbonate is 2-, and we have 3 of them. So our total negative charge here is -6, which means our total positive charge here has to be +6. Since we have 2 that makes up +6, we know in this case that each iron ion has to be a 3+. So hopefully that makes sense there. And then we would write down iron 3 because of the 3+ next to iron in this case. So the rules again are very simple. We name the anion, we name the cation, but then don't forget with multi-charged metals that we also have to put down the Roman numeral for the metal. We can't just leave that out. Okay, one of the things you'll notice here is that in the top problem, NaCO3, we did not use parentheses. In the bottom problem with iron, we did use parentheses. And those rules can be kind of tricky. Why do you use parentheses sometimes? Why do you not use parentheses other times? So I wanted to go over those rules really quickly. Yeah, and this just says that the anion looks weird, which is true. The anion does look weird, but the rules are still the same. Okay, when do we use parentheses? The simple answer is you only use parentheses when you have more than one polyatomic ion. That's the rule. That's what you're worth writing down. But that might be a little confusing to you. What does that mean, more than one polyatomic ion? Because there's numbers all over the place. So here's what I've got for you. I've got 3 examples of written formulas. Some of these are written correctly. Some of these are written incorrectly. Take a moment and take a guess. Which one do you think is written incorrectly? NaNO3, CaNO3, or AlNO3? Hopefully you notice that with Ca and Al here, I have 2 NO3s, so I would put parentheses. Here, I have 3 NO3s, so again, I would use parentheses. With this first one right here, I just have 1 NO3 polyatomic ion. So these 2 over here with Ca and Al have more than 1 polyatomic ion. Here we've got 2 polyatomic ions, and here we have 3 polyatomic ions. So these 2, we need parentheses. With this first one, we don't need parentheses. In fact, we would normally write it like NaNO3, just like this, where our NO3 is just kind of alone and by itself, no parentheses. And these other 2, Ca and Al, are written correctly. Another thing I'll see sometimes is people will get permission to use parentheses, and then they'll start putting parentheses everywhere. So here again are 3 more examples of problems, and I want you to see, are parentheses used correctly here? Are parentheses used incorrectly? Great. For the first one, you'll notice that parentheses are not used correctly. We never put parentheses around an element. We sometimes put parentheses around a polyatomic ion, but never just around an element. So in this case, how you would properly write this is you just write it as Na2SO3. SO3 does not need a parenthesis here because there's only one of them. SO3 is called sulfite, so it's its own little thing. That 3 is needed. If you take this 3 away here, you have something that is not sulfite, and that is not what we want. We want SO3 in this case. For Ca in parentheses SO3, parentheses once again are used incorrectly here. Instead, how we would write this is just as CaSO3. You wouldn't need parentheses around SO3 because you only have one of them. For this last problem, some parentheses are correct, some parentheses are incorrect. In this case, the Al parentheses are the ones that's incorrect. So we would write this as Al2 SO3 in parentheses 3. So in this case, we have 3 SO3s, we have 3 sulfites. Whereas in the other 2 cases, we just had 1 of these SO3s, 1 of these sulfites. So hopefully you see here why we still need parentheses around the SO3. Otherwise, if we didn't have parentheses here, if we just kind of scribble those out, you might notice that it kind of would almost look like SO33, which is not what we want, which is not true at all. Lastly here, we have a polyatomic ion OH. OH is called hydroxide. A little bit different, because now OH here has it has no numbers next to it. So all of these are actually correct. Sometimes what you'll see is you'll see people write something like CaOH, and then they won't put in a parentheses here. they'll just put a little 2 right there. This would be incorrect. CaOH2 with no parentheses or AlOH3 with no parentheses would also be incorrect. You need the parentheses here because you have 2 of the OHs. If you put OH2 without the parentheses, then you have 1 O and 2 H's, which is a totally different compound. Great. So I hope this helps you guys start to understand some of the polyatomic ions and stuff like that. I'm going to leave you guys with a couple of problems that you can try out on your own. Great. Here are the answers to those problems. Just kind of going from compound to name. Again, what I want you to notice here is notice where the parentheses are. These are all correctly written formulas. So in this case, we only have 1 OH and 1 SO3. But we have 5 PO4s here in the last problem, and PO4 is called phosphate. Great. Hopefully this helps, guys. Thank you for watching, and have a great rest of your day.